Hello, ladies and gentlemen. Welcome to my presentation. Today, I'm going to make an interpretation about my master thesis introduction about my master thesis, which is metal decorate carbons for electrochemical CO2 reduction. And Christian is my supervisor. So, first, I would like to talk about the motivation. Why we want to reduce CO2. If you take a look at all organic chemical, and you will find the Gibbs free energy of the CO2 is the lowest. So it also means we cannot gain any energy from CO2. So we want to reduce it to whether from acid, methanol, carbon monoxide or something. And you may heard about 30,000 times that CO2 causes greenhouse effect and so on. So I won't talk about it anymore. So then why we want to use carbon as our supporting material, also to say heterogeneous catalyze for electron reduction. So there are many other options. There may be metal organic frameworks, metal oxide, solid gelation, and so on. But among them, some may tell you that the carbon is cheaper than those. I will tell you no, that not. This why we use carbon is carbon has the electronic conductivity, so it's easy to gain electroconductivity, and in the meantime it is easy to get get a porous, and other they are whether hard to gain porous or hard to gain electroconductivity at the same time. Then I I'd like to show you about my plan of my master thesis. I'd like to distinguish it into three parts. First, synthesis. Uh, what we need to do is calcination, then maybe use some acid, not maybe, we must use acid to wash it, and then impregnation. After that, we may do another calcination and acid washing. So 3-step: calcination, acid washing, and impregnation. And characterization, we need to use powder X-ray diffraction, BET surface analyze, scanning electron microscopy, energy dispersive X-ray. I forget whether it's microscopy or spectroscopy. I forget about it. Then the X-ray photoelectron spectroscopy. The last part is electrocatalytic performance. We need to use the linear sweep photometry to test the electrocatalytic performance, and we need to use gas chromatography or nuclear magnetic resonance to test the product we have. So let's go. Synthesis. How do we get the supporting materials, also called carbon acid material? And we need organic precursor. Here we use a granine, and we need to mix it in some salt. We may use the calcium chloride or magnesium chloride, and we calcinating them to 800 degrees under the protection of nitrogen atmosphere. Then we get a mixture of carbon acid material and the salt. In order to strip the salt, we use acid to wash it. Then we get our black carbon powder and nitrogen dot inside. So what do we expect from our carbon? So the supporting material, it should be randomly aromatic, 5 ring and 6 rings. There are most of them are carbons, and some sides are nitrogen. They may have local graphite structure, but only in a very small range. Then it is amorphous materials. I like to say it's not a crystal. So the how to say the order? No, not the order. The provide the evidence is here. If we take a look at the powder X-ray diffraction, we say no sharp peaks, and the sharp peaks means interference. So this layer and that layer, it don't have the constructive, how to say that word? Constructive interference, I believe that's the word. The bright, the brighter, the bright of the light. So then we take a look at the scanning electron microscopy, and we also say no sharp edge. Sharp edge is a signature for the crystal, for the how to say isotope. So isotope. Isotope is Deutsch. I don't know how to speak in English. So let's go. So it should be enough. Then synthesis, how to make the metal anchor on the carbon skeleton, how to make the real catalyze deposit on the carbon skeleton, carbon supporting material. The answer is impregnation. We use the carbon skeleton. Now we have already got our carbon skeleton. Then we add some metal salt in and add some solvent in, make it homogeneous mixture. Then there are some way to do that, several way. First, thermal decomposition. The ligand of the metal reduce metal ion to metal element under heat. It may happen and may also have the metal oxide. I'm not sure whether we have the metal or metal oxide active side on our carbon skeleton. I'm not done that far yet. Then chemical reduction. What we have metal salt, which is metal ion, and we need to reduce it. We need some reducing agent like vitamin C, carbon monoxide, hydrogen, and sodium borohydrate, I believe, hydrate, yes. Then we can also use the electrochemical synthesis, use the calcite to provide the electron, and we can also use radio, sonar, and so on. I didn't check a little literature. I didn't check the literature about this part. So in this part, we need to know the electron cannot be poof there, or poof gone. Yeah, we need the electron must come from somewhere. Yeah. The next part. Then we need to test our electrochemical cell. First, we need to set up a cell. The setup of the cell is like this. We can say under there are working electrode, reference electrode, and counter electrode. And if we which are soaked in the electrolyte solution. And if you can see, there are also holes for degassing or reagent addition. So one of the holes should be adding the CO2, and another should be go to the chromatography, NMR, and so on, maybe. Yeah. And we need to know what happened or what may happen there. First, what we want is CO2 reduction reaction, CO2RR, CO2 reduction reaction. We can say the CO2 and water under the aqueous surrounding, and some electron will go to maybe carbon monoxide, carbon monoxide, form acids, and so on. And in the same times, in the aqueous solution, aqueous surrounding, it also happens hydrogen evolution reaction, HER, which is two of the proton may gain to the electron and go to the hydrogen. Yeah, and when this thing happen, you can see the bubbles appear just poof there on the working electrode. Yeah. Then the next day, okay, forget about it. Then the electrode performance of liner sweep voltammetry or cyclovoltammetry. For the introduction presentation, I use this page first because I haven't get any data from it. So this picture is not the CO2 reduction reaction, but it will be very helpful to understand the liner sweep voltammetry for CO2 reduction reaction. So let's assume the black line is for the metal-free carbons. And the first peak is for the hydrogen evolution reaction, and the second peak is for the CO2 reduction reaction. And these lines should stand for our metal-free carbon-acid materials. If we deposit some metal or metal oxide, which is real catalyzed on them, what do we expect? So it should be inhibit our competition reaction, which is hydrogen evolution reaction. So the first peak should be lower, and then we need that to promote our CO2 reduction reaction. So the second peak should be higher, and third, with lower overpotential triggers the CO2 reduction reaction. This peak will shift to the lower overpotential. So it will look like this, the red line. Yeah. This peak is not for the CO2 reduction reaction. Yep, remember it? But it will helpful, very helpful. So last but not least, I'd like to make a summary. First, synthesis, organic precursor, and salt calcination. We got a dense material or the mixture. Then we use acid to wash that mixture. Then we got the carbon acid materials, and last but not least is the impregnation. We add some metal, salt, and calcination it again. So it's then we got our metal decorated carbon. Then the second part is characterization. We use powder X-ray diffraction, BT surface analysis, scanning electron microscopy, energy dispersive X-ray spectroscopy or microscopy, and last and the least is X-ray photoelectron spectroscopy. Yeah, and the last part is testing the electrocatalytic performance. We need to test the liner sweep voltammetry, cyclovoltammetry, and we use the gas chromatography and nuclear magnetic resonance for the product detecting. So as far as I know, the electrocatalytic performance is much cheaper and quicker than some of the characterization like EDX and XPS. So we may first synthesis a lot and test the electrocatalytic performance. Then we pick the good 1, 2, or 3 samples to the characterization. So this shouldn't be. Thanks for your attention. I hope you enjoy my presentation. If you like my introduction, don't forget to subscribe my channel, although it's not a YouTube channel. I'd like to answer your question if you want. I've been prepared really a lot. If you can see, yeah, I've been prepared only how many 11 slides for the presentation, and I've been prepared, if you can see, 30 slides for the question. So I'm very happy to answer the question. Thanks for your attention. Question, please.